Hello everyone, this is Professor Jeff Wilkerson at Luther College with an introduction to exercise 7, the image size focal length relationship from Astronomers as Observers and Experimenters, published by Kendall Hunt, introductory laboratory exercise book in astronomy. So this exercise is really what it says. It's all about finding how the image size that's produced on a CCD camera is dependent upon the focal length of the imaging system that's doing that imaging. And you're going to work with these images of the moon and work through here, measure the diameter of the moon, and then measure the diameter of the moon, remembering that this has been blown up 2 times. It tells you in here that the prints are enlarged 2 times, so that this is actually twice the actual image size of what you get. And then you can look at that and you can say the moon is a ½ degree across, and we want to know how much 1 degree of sky, so per degree of sky, that's the way to think about this, is what's the image size per degree of sky. And then we're going to walk through how to convert this. This is an old way of thinking about doing this with film, and we're going to walk about through how to do this with CCD cameras as well. So the lab walks you through that sort of exercise. I would, as almost always with all of these exercises, I would use a digital caliper to make these measurements. So you can just get your digital caliper, go in here and measure the diameter of the moon in each of these images and figure out what the diameter of the moon is there. And you've got your scale, then you've got your size of the moon right here. And knowing that that's a ½ degree, but that's also been blown up 2 times, you can convert that to say, okay, what would 1 degree of sky look like on this film, on this image that we have right here? As it says in the exercise, by the time you get down here, it's pretty hard to measure the diameter of the moon, and you better measure a crater in this last image and compare it to the size, scale it to the size of a crater up here. You could probably do that with a mare, one of the dark regions. Look in here and see that down in here in the lower right, that's these dark regions. That's the mare that you're seeing right there with that bright nip between them is right there, and that bright dot right there is right there. So you might even be able to get away with measuring the size of that bright dot, but you can probably scale from there to start to find craters that you can use along across in here. And so that's what you want to do to measure the diameter of a crater here and say how many times bigger is it than that diameter that you had in this set of images. And then you can use that to say, the focal length, given that focal length change, that's telling me what the size change, what the image size change is as a function of focal length across there. You graph this relationship up and fit a line to it, and that's going to give you the slope of that line is going to give you your image size focal length relationship. Now, more commonly, the way you're going to use this is to convert that to something like arc seconds per pixel is a great way to think about how do you take that information that you just have and convert that to arc seconds per pixel in a digital camera. So if you've got an array that looks like this with lots and lots and lots and lots of pixels in it, you can ask how much sky does each pixel cover? And then if you multiply by the number of pixels across a dimension like that, that tells you how much sky you see across this direction. So in a way, it's thinking about inverting this relationship to say that your image size is now your pixel size. And if you take your pixel size as your image size and then turn that back and solve that for the angular extent on the sky that you see with an image size of that size, you can work backward and say, okay, with this focal length, I'm going to see this much sky in a given pixel and this much sky across a field of view. And so you can start to work out this relationship. What I would typically do when I work with my research students upstairs, we're taking pictures of the night sky. We're taking pictures of the same patch of sky for a very long time. And over 2 decades now, we've been taking data from this field of view that you see right there in front of you. And I know, so this is an interesting field. There's lots and lots of stars, a very confusing field to get a handle on. And so you look at that and you say, well, okay, how are we going to figure out the image scale? How are we going to figure out the scale of what we've got going on here? And the way we do that is these stars, it's very busy, very difficult, but some of the stars form bright patterns. The brighter stars form patterns that we can see in the data in here. And we can identify certain stars in here that we know the right ascension and declination. We know the celestial coordinates of certain stars in here. The brightest stars in this field of view are about 9th magnitude. The majority of the stars are 14th magnitude or fainter. There's about 1,620 stars that you can reliably see in a 70-second image in there. And so it's a busy field, but if we can identify patterns, we can say the right ascension and declination of that star and the right ascension and declination of that star, then we can use our knowledge of how angular separation depends on right ascension and declination. Generally, the field's small enough we don't have to do real spherical geometry. We can use simplified forms for that formula, and we can calculate what the angular separation of those is. And we can say, and then we know the pixel position of this and the pixel position of whichever star we were looking at over here. So say it's those two stars, we know the pixel positions of those two stars, and we take x minus x squared plus y minus y squared, x1 minus x2 squared plus y1 minus y2 squared, all square rooted. And that's going to give us the separation in pixels between those two stars. And if we know the right ascension and declination of each of those two stars, that gives us the angular separation in arc seconds or arc minutes. And say, so we'll have a number of arc seconds is equal to, that's the angular separation we measured from their known celestial sphere coordinates, is equal to so many pixels as calculated with that difference right there. And so that's what we would do, and we would get so many arc seconds per pixel. When we do that with our field of view and our camera upstairs with the data that we've been taking, we get that this is just under 30 arc minutes across there, just under half a degree per side. So we got about a half a degree per side is what we get with all of our 1024 by 1024 pixel array across there. We have big pixels in that camera, and that we have to talk about why at some other point. But to say, okay, we've understand what our field of view is in our sky. And so this is important for us for a lot of reasons. Every now and then we see an asteroid move through the field of view. We want to know how fast that asteroid's moving. And if we want to know how fast that asteroid's moving, we got to know how many pixels it covers in a certain amount of time. We got to turn that into an angular distance. But also we got to identify every star in this field of view. And so we got to know from what the right ascension and declination is of a few of these stars, we got to be able to get that for all of these stars. And so we can work the other direction there. So we use this information a lot. This is a very, very powerful tool for us, a very important tool for us, thinking about sort of plate scale, image scale that we talk about in this exercise, to think about what's the scale of this image. We use it very, very useful information. We just have to know how to do it in order to work on the projects that we're working on. So you can think about this in terms of learning goals. So first, a confession here. I'll straight up confess, I've never done this exercise with students. I've worked through this exercise on my own. I've worked through it. I've had my research students look at it and work on it a little bit as we're doing the kind of work I was just describing to you. But I've never done this in a classroom setting where students and I have sat down and worked on this together as part of a lab, as part of a teaching laboratory experience. So I don't at all. I don't typically use this exercise, but I think about learning goals that are really valuable in there. And in addition to just understanding optics and limitations of telescopes, to say there is a trade-off for our project. We want to see a lot of stars, a lot of stars. So we want a bigger field of view. We could get a bigger diameter telescope, and with a bigger diameter telescope, we could see fainter stars in a shorter amount of time, but we would have a smaller field of view, and that wouldn't be as good for us. So we want more stars in there. We want a wider field of view, but it's a trade-off. You don't want to. You have to be able to gather enough light to see some fainter stars in there. So we have this sort of trade-off. So thinking about those trade-offs helps us pick the equipment that we want to use to do this. And it's also then, if you're out there thinking about buying a telescope for your own personal use, you'll often read that a refracting telescope is better for solar system objects. If you're really interested in looking at the bands on the surface of Jupiter, or interested in looking at the rings of Saturn or the moons of these planets or so on, If that's your primary observing objective, then often you'll read you want to get a refracting telescope. And there might be multiple reasons for that. But one of those is you have a smaller field of view, a bigger image size. So you get a bigger image there and not as much field of view. That's great for looking at the things we were just talking about. But if what you're really interested in is looking at big galaxies or other things that are beyond the solar system like that, seeing deep into the sky and looking at sort of nebulae and stuff like that, you probably want a bigger field of view and a little bit more light gathering capability. And so it's a trade-off that you have right there. So it's good thinking about that. So one thing is understanding that relationship. All of this is about what your learning goals might be for completing this exercise. And that's one of the things is understanding equipment and limitations of equipment is a very, very valuable learning goal to have as you approach this work. Another goal is to think about the process of science itself. And we have really been emphasizing that in this video series and in the textbook and other places. You call me on the phone and I'll talk to you about it forever. So I don't recommend that you do that. And the idea of this process of science, saying it's real people doing real things, working on scientific projects and trying to think about how to make this thing work and how to make this thing go. Part of that is calibrating data and doing the very, very detailed work that we were talking about here to make sure you understand every single star in this field. Which star it is. You don't confuse star A with star B. That can't happen. Okay, in a project like what we're doing, you got to know which star is which, and you got to know where you're looking and what you're seeing when you look there. And so really taking the time to do this right and to align these images to a reference image. Always, that's the reference image that we use for our project, our 20+ year project. That's the reference image right there. We align all of our images to that image and do the work that way. That's part of the detailed process of what it means to do the science, to figure something out. And if you don't cross all those T's and dot all those I's, your chance of success gets to be very small. And so this is a really good exercise for a reminder of the importance of that work. So that's what this exercise is about for me. You may have other goals as you look through it, and you may be interested in this for other reasons. But that's what I think about when I think about this focal length image size relationship that you're working on here. I hope you find that project interesting. You find the exercise interesting, thinking about sort of these trade-offs and these things that you can do. And I hope you have good luck working it. Let me know if you have any questions with it. Thank you, everybody.